Welcome to today's explainer. We are going to totally reframe how you view entropy. Instead of seeing it as this cold, rigid law of physics, we're going to look at it through the lens of system architecture. Because as you'll see, it actually acts as a highly subjective, distinctly human-centric design choice. It's going to be a fascinating ride from the human mind straight down into the physical machine. Okay, let's take a quick look at our roadmap for today. We're covering 1. Redefining entropy and information, 2. 3 dimensions of perception, 3. The logarithmic math bridge, 4. Binary versus decimal systems, 5. The cost of miscalculation, and finally, 6. The architect's ultimate authority.
All right, diving right into section 1, redefining entropy and information.
Most folks just assume entropy is this super strict objective metric of physical chaos, right? Well, actually, scratch that. We need to completely dismantle that illusion of objective physics. Entropy is in fact a highly subjective tool. It provides a numerical value that only sort of explains organization. And that incompleteness, that's entirely intentional. It's a metric based entirely on how a human observer decides to parse a system's parts. Just look at this quote. It absolutely hits the nail on the head regarding this massive paradigm shift. It tells us that entropy doesn't live in the physical hardware at all. No way, it lives entirely in the mind of the observer. It's a reflection of human organization, meaning it's all about the specific way that you, the architect, perceive a system through its constituent parts. So, if the organization is subjective, then the entropy itself has to be subjective. Which brings us to section 2, 3 dimensions of perception. So you might be wondering, how exactly does a human architect's mind actually dictate all these components? Well, human perception happens across 3 distinct dimensions. First up, we've got granularity and resolution, basically the zoom level. The observer decides how small or large the individual parts are. Second, there's boundary selection. This is where we decide what belongs inside the system versus what gets dismissed as just environmental noise. And third is temporal persistence. This is where we establish the criteria for what actually constitutes a change over time, deciding which fluctuations matter and which are completely negligible. Moving right along to section 3, the logarithmic math bridge. Okay, so once we've defined our qualitative human perception, we have to transition over to quantitative rigor. We need to actually build functional systems, right? So information is calculated by mapping perceived states into a manageable symbol set. And in this rigorous framework, information is defined logarithmically. It's roughly equal to the log base of the states. Without this exact mathematical translation, architects would quite literally just be guessing at the physical resources required to describe a system. To put that into perspective, let's look at how this math actually plays out in reality. Say your perception defines a massive, sprawling system of 1,000 distinct states. This logarithmic calculation elegantly compresses all that astronomical complexity. If you're calculating in a binary base, the log base 2 of 1,000 is roughly 10. That means your vast logical system is mapped into a totally tangible, manageable physical budget of just 10 bits. Now, the absolute key takeaway here is that a linear, one-to-one symbol-to-state mapping, it's completely unsustainable as complexity grows. Think about it. If every single new part you identified linearly required a whole new dedicated physical resource, our machines would be infinitely massive. Because state complexity increases exponentially as new parts are identified, we absolutely rely on logarithmic scaling to tame these systems and design hardware that can actually store and process all this information. Now for section 4, binary versus decimal systems. So we have to drag this mathematical abstraction out of the clouds and down into physical reality by picking a numbering base. Take our 1,000 states again. Choosing binary, or base 2, demands about 10 symbols, but it relies on incredibly simple high or low voltage hardware. On the other hand, choosing decimal, or base 10, requires only 3 symbols. Sounds great, but it demands highly complex hardware logic to safely distinguish 10 distinct states per single symbol. It's really like a high-stakes balancing act for the senior architect. You are constantly trading off the sheer information count against the actual physical medium of the machine. Binary gives you a higher information count, but a much easier medium to work with. Decimal gives you a lower information count, but demands incredibly complex physical logic. This crucial translation from a numerical base back to the perceived state definition completes the whole cycle of information architecture. Next up, section 5. The cost of miscalculation. So what exactly happens if the architect's initial human perception is just wrong? Well, if you fail to perceive critical parts, you get architectural underrepresentation. That gives you an insufficient symbol budget, which leaves your system entirely unable to capture its true operational complexity. Essentially, it's broken. But on the flip side, perceiving parts that aren't actually there causes architectural overcomplication that bloats the state count and wastes incredibly valuable physical resources for no reason. And here is why this is absolutely crucial. Because the formula linking perception to hardware is logarithmic. A simple human error in perception doesn't just create a tiny linear mistake. Oh no. A slight misjudgment in your zoom level or your boundary selection profoundly and non-linearly shifts the entire scale of the physical architecture you're going to need. Finally, we arrive at Section 6, the architect's ultimate authority.
This whole incredible journey from abstract human thought straight down to hardware really boils down to three crucial takeaways. First, state counts are a direct output of human perception, not an intrinsic property of the hardware. Second, entropy is an entirely subjective metric for organization. It's totally incomplete without human boundary selection. And third, resource allocation scales logarithmically, meaning even minor perception changes will massively impact your total information requirements.
Basically, information isn't just floating out there as some objective constant of the universe. It's a function of human perceived organization and the specific mathematical base selected by the designer. The architect holds the ultimate authority here. By actively selecting the boundaries of perception and locking in the math, they, and they alone, dictate the information that literally brings the system into physical existence. So I want to leave you with this final, somewhat mind-bending thought today. If the tangible, physical constraints of our most incredibly complex machines are actually entirely dictated by subjective human perception, what else in our supposedly objective reality is merely an illusion of design? Think about that as you look at the systems all around you today. Thanks so much for joining me on this explainer, and keep exploring.